what I'm showing here, I'm not an expert in this library. Okay, I'm not developing this. I'm contributing a little bit to something they're doing, especially in the standard, in the C++ standard committee. We mentioned that at some point. This library, Kokkos, is developed at Sandia National Labs. And I think it's a very interesting library for HPC. So these guys run HPC applications all the time. Okay, so Kokkos comes from the Greek word for granule or speck. I hope there's no Greek person here because I don't know if that's true. But it should be. And the idea is to identify the smallest grain of computation you can possibly have and aggregate the grains into bigger computations and map this pattern to the architecture, computation, and memory, and run it as efficiently as you can. This is, I would say, a quite well-accepted model. I've been working with this model since many years now, and the grid tools is actually an implementation of that model. If you think of a stencil, applying the stencil function to a point, and you can do this in parallel to all the points, the smallest granule of computation is the stencil function. So grid tools, in some sense, is an instance of this thing, of this concept of specifying the maximum parallelism you can, aggregate the thing, and run in chunks. So to avoid the threads overhead or the things or runtime overheads. They support CPU, Xeon Phi, NVIDIA GPUs. They are more active on the backend side, more than the grid tools. And as API, each API has concepts or major structures. So for Kokkos, the major structures is the memory space, where there is where data lives, layout, how the data elements are mapped to the memory, the execution space, so where is executed, where are the cores, where are the functional units. The execution policy is how are these functions being executed? It'll be parallel, sequential, parallel, or other ways. We will see probably if at time some example. Then you have the pattern. They call the pattern the algorithmic motifs. What I call algorithmic motifs, they call it pattern. And when you call something, it would say pattern execution policy. I mean the policy on this space. So execute with this policy on this architecture, and run these functions with this function with that data, which is also happen to live in some memory space. And this is like parallel for, parallel scan, all the usual patterns. One thing that Kokkos offers is multidimensional arrays. And here we can open little parentheses. C++ does not support, well, multidimensional arrays. And this is what every Fortran programmer will always tell with a little bit of, superiority coming in and say, yeah, but you don't handle multidimensional arrays. It's true, we don't. So Kokkos library tries to provide a powerful interface for multidimensional arrays. Part of this thing has been proposed to the C++ standard committees, and and it has been well accepted in the last meeting. So there is hope that something like this will be supported in C++ 17. We cannot tell, of course, nothing now, but hopefully something like this will be available in the standard C++. What are the ideas that Kokkos offers is a polymorphic polymorphic layout for multidimensional arrays. What is a layout? A layout is a mapping from a tuple of indices to an offset in memory or to an address in memory. This mapping is usually an affine mapping. It's like an internal product between strides and indices. If you go to a Fortran style, you get the first dimension with the stride 1, then the second with the bigger stride, and the third with the big stride, etc. In a C, the last one will have stride 1, and they call this layout left and layout right. But you can have other layouts. You can have a tiled layout. A tiled layout, if you look at it, you have a two-dimensional array with tiles. It's like a four-dimensional array in which the first index represent the tile. The first two indices represent the tiles, and the second indices represent the element within the tile. So we have four indices to map one element to this guy. But as a two-dimensional array, you need a function from ij to this guy. And from ij, you go to should be something like I number of tiles on I, j number of tiles on j, I reminder, something like this. I don't know, I might get this thing wrong, but the gist of it, you need to do a division and a kind of modulo operation. It's not the modulo because it is actually a reminder. But so a map from two-dimensional to four-dimensional, this is an affine map now. So, you can have symmetric layout. You want to store only the upper thing, and you want to go from ij, that if I is greater than j, it's okay, otherwise you swap and you say ji. That's another mapping. This is non-linear mapping. So it's very general idea. You get the space of indices and you map to the thing. The problem is different memory systems have different layout, different best layouts for your computation. It depends on the memory, or how the memory is organized. It depends on the execution space, on how the threads are actually executed. It depends also on the pattern in general. For the patterns in Kokkos, I think it wouldn't matter too much, but in general, it depends on the pattern. And the thing is that the layout should be known at compile time, right? When you write Fortran code and you do a multidimensional array, or you write C code, and you have a multidimensional array, what you get is that implicitly you know the mapping. It will be something like this: the offset, L, okay? The offset is the stride in the ith dimension times the index in that dimension. And this gives you the offset in this array. So it is known at compile time usually. Maybe you don't think about it. So is it possible to interchange these functions? You compile with a different mapping function and you get a different behavior of your application, changing just a single line of code, just the line that specifies the layout. Actually, yes, and Kokkos does it, and Grid Tools does it in different ways. I would do it. So Fortran will be S0 is 1, S1 less than S2, S2 less than S3. C is S1 d minus 1 is equal 1, and sd minus 2 greater than sd minus 1, etc. Right. But you can have all possible permutation. You can just take this thing and turn it around. What is the point? That the ijkl there are just logical indices to your elements in your array. They're logical indices. They say, I want the element ijkl. Where is it? Well, I need to know the function. I cannot tell you before I watch the function. But if I tell you the function at compile time, from there on, everything is decided. So what you want to do is write an algorithm in a layout oblivious way. So you don't want to write the algorithm in a way that to expose the layout, or at least you might expose the layout at compile time, like specialize some functions. That you can do it. But you want to write these things in a high level. You don't want to see the layout. You want to specify the layout, but you don't want to see it afterward. So in the best case, you just change a single line of code, and everything will be remapped in your application. In other cases, you have a few lines probably specifying layouts, and you need to change all of them. Also, another thing, how much time do we have? I need to cut down some of the stuff. Let's go see layouts. Let's go to see layouts first, because I want to show you also how grid tools do layout. So is Kokkos simple. Let's go back here. Is it simple? Yes. Kokkos simple view offset. This is not the super updated code. They are in the middle of changing some of the API. So don't take this as the final thing. It's just an example of how this thing can be implemented. So, oh no, wrong one. Layout is in. Oh, view offset, yes, okay. So view offset, yes. 57. Okay. What do we have here? Is a template, declaration. A view offset takes the shape type, which is the shape of your array, the dimensions as such. You have a layout type, and then we have well, no, that's the enable thing there. Is like it's just for sphenae. And then, so this is empty. So you cannot instantiate this guy. But you can instantiate this guy. You have shape type, whatever shape it is, and layout at left. Layout left is a tag type. The tag type, well, I don't have time to search for it. The layout type is a struct layout left using layout type equal layout left. Can you read it? It's an empty struct, basically. It's an empty class with name layout left. It just contained a layout type equal to the same type, just in case someone passes me this object and I say, what is it? Well, it's layout left. Okay, I can, if someone gives me type T of something which is a layout and I do layout type. Then I get this guy, all right? Just for, when you write generic code, usually you have to expect someone passing types to you, and you need to be able to know at compiler time what they are. But this is an empty struct, which enables this specialization. Okay, so this is just to say, when you get the left layout, this is the thing you need to do. And there's an enable if, which I show you the enable if example early, or did I? Did right? It's just a way of enforcing that certain invariants are valid. Otherwise, the compiler will tell you, will give you an error. I want to go into this thing, but this is the kind of thing you might want to do at some point. Assign. So the real interesting function, okay, should be around, quite down there. 200. There are many constructors, and here it is. So look at this. Many functions with the same, more or less the same form, that given the indices gives you back the offset for that guy. The layout right will be very similar to this, only that these guys will be switched. It will be N3, N2, N1, N0. Okay? And you have different things for different dimensionalities of your functions. And they're all templates, so they're instantiated only when they're used. So layout left. Okay, for another case. Anyway, I think you get a gist of it, right? This is the biggest one. You have a 7-dimensional arrays, and this is how you compute the offset given the indices. And so you have another class like this, quite big class, to do the layout left or the layout right. In grid tools, we've chosen a different abstraction. The abstraction we've chosen is in common layout. Go to include common layout map. It should be the first, should be the C++11. The template, the layout map type, contains a variadic list of short integers, which represent the permutation of the indices you need to apply to this guy. Right, it should be like ki, and this is the permutation. So you write there the list, the permutation of the indices. It's all done at compile time. There are data members, but they are static const expr, so they're only available at compile time. When you compile this thing, this goes away again, and it is used. Let's see if I find it in storage, meta storage based 324. Why did I want to go there? Let's see. Okay, so we have a vector of strides. We call it index, it's just the offset actually, but I called offset before. And it does, okay, go to the layout map, find where the first dimension is, which has the largest stride, by the way. So the strides are sorted by decreasing order. I might be wrong, but it just doesn't really matter. So the strides are ordered in decreasing order, and you get, give me the dimension, which is 0, which has the largest stride. And from the set of indices ijk, and do the second one, and do the third one. So with a single function, with only these lines of code, we can deal with every possible layouts, affine layouts. Okay? So, questions? Clear? Yep.
In the Kokkos library, you showed us the layouts and the shapes. Are those the ones that are being submitted for the standards, or is that different from the array views?
It's quite similar. Similar to that. Yes. It's just an implementation. You know, I mean, what matters for the standard is the API. I mean, the implementation can be tweaked and improved, and probably we will improve it. But yes. But basically, if you go, I don't know if the implementation is public, but there is an implementation of that thing which is basically similar to that. It's slightly, it's better, but it's similar to that. So the layout is a tag type, which somehow I don't like it, but it's really flexible, really, because you can, with a tag type, encode every possible layout you come up with: Hermitian, symmetric, three-diagonal, whatever, right? So you can do everything. Please.
But I mean, so the array view, the proposal for the array view has the same interface. So
similar. It's not the same. Okay. It's not the same. Actually, I'm showing you now the interface that Kokkos has. The interface proposed to the standard committee is not the same, but it refers to not to the layout but to the shape. So the layout is basically very, very similar, but the shape, it will be totally different. So what Kokkos has right now is not the one that goes into this proposal. It has some limitations and some semantic issues. And actually, this is what I wanted to talk next. Yeah?
Does it now mean that whenever you use this in type, you go through a lengthy calculation to find the element?
A lengthy compile time computation. So when we iterate through, so we take the plane, ij plane usually, so on the host, you take the ij plane, and you move to some point in the 0 dimension, and then you increment the pointers there. So you do that layout stuff only once on the outer loop. So the innermost loop is still with +1 on the pointer. And yes, there are several functions. So you instantiate the offset tuple, you add these numbers to something, you call some other function. They are all inlined, and they goes away. And the performance is really like accessing raw multidimensional arrays. I know it might be difficult to believe sometimes, but it does. It works pretty well. Okay, a few minutes. The view. The view is a concept that has been around for at least 15 years or more. The view, you take a bunch of memory and you build a view on top of it. You see that memory as something else. You can see a linear array of elements as a multidimensional array. The view, though, has a special semantics. When you copy a view, you don't copy the data. So it is called shallow copy. So it is efficient in a sense because you create a new object pointing to the same one, which is basically a reference semantic. Slightly different because you can create a different view from the same data, right? So you can You can change the layout when you create a new view on the same data. So it's not really a reference, but it's almost a reference to the data. And the view has a shape of the, in Kokkos, dealing mostly with multidimensional arrays, a view has a shape, has a layout, has a memory space. Just to point out, in the future especially, there will be more memory spaces than there is now. You have scratchpad memories, you have a fast non-volatile memory, you have RAM memory, you have GPU memory, share memory, const memory, texture memory, all these things. These memories have different trade-offs, so memory, speed, bandwidth, latency. So memory space is just there. You can basically customize your view. You can put your data in any of those things and can manage yourself. And it's very important. So if the layout is not specified, fine. Kokkos will choose it for you. But then is the array shape. So if you say double pointer, 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 open, close, 73. This is a 7-dimensional array, which 5 dimensions will be known at runtime, and 2 dimensions will be known at compile time. So the 70 and 3 will be known at compile time. So it is important many times to have loops, bounds that are known at compile time, so the compiler can do vectorization easily. And you can do alignment also if you encode the memory space in the right way. You do alignment, and you have all these nice features. Again, this I1, I2, up to I7 are logical coordinates. There is no clear relation between, if I increase I7 by 1, what happens? I have to see this map to know. But my algorithm is written in a way that it doesn't have to matter too much, because I'm using a pattern. So I'm using it for each. Hopefully we'll get there, maybe not. So for the purpose of this interface, pointers and empty brackets are the same. No, just to show you, you can do both. But you cannot put this one here. You cannot put this one here. So the compile time version should be at the end. And this is a limitation that that you're trying to overcome with the standard committee proposal. How does it work? So first of all, we need the concept which is integral constant is a class which has a static constant value of type t. So integral constant int 7 is just 7. And this is a compile time. A static assert is evaluated at compile time. It's just a number, the number 7 at compile time. I need it just for the example. So when you do this, you have a type of 3, an array of 3 elements of arrays of 4 elements. This is actually a T, an array of 3, T3 parentheses 4. So if I pass this guy to something, so the standard library has a rank function. It does class T, and it takes the dimensions of an array. And you can do, if I give you a type T, the rank of that guy is 0. So it's static integral constant 0. Inherits from that. If I pass a type which is a Tn, the rank of this array is 1 plus the rank of the T, or whatever T is there. So T in that case will be int of 3. So it will go again, it will add 1 until it goes to the last element, and we create a 0. Is it clear how this works? And this works also for pointers. So this gives you the mechanism that to get the double and the pointers, brackets, and etc. How this is implemented in the Kokkos to describe the shape. I don't have the time to get into it. I want to let John show you some of the HPX. And I guess, yeah, we're basically at the end of it. Yep.